We're going to be doing the AVL assignment. This is to populate a tree via a text file, input.txt, and make sure that after every insert, the tree is balanced. At the end, we're going to display the tree in level format. We're going to make sure to include the height and the balance factor of each node in our output. We can redirect this to an output file if we want, but for our example, we're just going to be printing it to our console. We have hints right here, and then more information about this right here. Both of these documents, the Word doc and the PDF, will be linked below the like button in the description. So you can look at both of these here. These are more rules, questions of how we would do this. So now we are going to look at the actual code for this. The first thing that we're going to start with is creating our classes. So we have our main class. And then we're also going to need to have a node class because we're going to implement linked list to make our tree. So we'll do class node, and then inside of here, we're going to have our data. This is going to be a little bit different from our other classes with nodes that we made previously. Those videos can be found in the playlist linked below the like button. Next, we're going to have our class, where we have our AVL tree. And now we have our node class, we have our main class, and the AVL tree class. We want to make an instance of this AVL tree class inside of our main method so that we can use the submethods inside of it. So we're going to do AVL tree is equal to a new AVL tree, and the tree is just a name for this instance. So this is what this will look like. Now, what we're going to want to do is we want to insert our file into our instance here. We want to insert it into our instance. And then we're going to want to print it. So we're going to need an insert method and a print method. We can do tree dot insert, or it says toString, that's auto-generated, but we want to do insert. And then inside of here, we're going to have our file name, and our file name should be input.txt. And then we're going to want to print this, so we're going to do dot print, and that should end that. Now from here, we are going to want to create a method that'll print this, or that'll insert this. And then we're going to also want to make a method inside of here that will print this. It's asking us to cast. That's not what we want. We want to make a new method called print. So inside of here, we can do a public and then a void because we are not returning anything. And we can call it print and then just encase this right here. Now the reason why we're getting this error right here is because of when we auto-generated this insert method. It should not be just an object. What we want is to have the AVL tree inside of here, because we are making a public AVL tree insert inside of our AVL tree, so we're kind of calling it, and we need that to print it outside of here, in here like this. And that's going to be it for our main method. Now we can look in our class node. Inside of our node, we are going to have a public int. We want our data. We also want the height. We're going to store that in here. Now we're going to also want the left and the right of this because we need to store that data for balancing purposes. So we're going to have node left and right. And now we're going to want our constructor. So for our constructor, what we're going to need is a public node. We are going to pass in our data, so it's going to be int data. Inside of here, we are going to do this dot data. So the data that we have up here is equal to the data that we are passing in. And then we're just going to set the height equal to 1 for this, and we can always increment this, add into it, or change it later for the height. And that's going to be it for our node class. And now we can look at our tree class. So let's start off with our insertion right here. All we're doing is we are going to run through our text file, and we want to insert this into our tree. We'll do this in a separate method that we'll call in here. So we want to make a new instance of this. We're going to have our AVL tree, and we're going to call it TRE, not the full tree, because we already have this instance up here. We could just call it tree1, either works. And then we're going to make our new instance, AVL tree. Now we're going to want to also have a throws file not found exception because we're reading a file into here. So we'll do throws file not found exception. For this, we don't need any parentheses. We will need to hover over it and import it though. That's important. Now inside of here is where we're going to want to read our file. We do have an error up here as well. Before we finish this, we're going to want to add either a try catch or a throws declaration. We could do a throws, and we would throw a file not found exception like we have down here, or we could do the try catch. So we're going to try to do this, and if this doesn't work, what we'll do is instead do a sysout and print out file not found, because that means we have not found the file. It's the only reason why this would not print out for a file not found exception E. Now coming back down to our tree, what we're going to want to do is again try to read this in. So we're going to throw as files not found exception. We're going to have our scanner file is what we'll call it, and we'll set this equal to a new scanner, where inside of here we want a new file, and we're going to open our string, which we'll just call it file name, so it's a little bit more easy to see if we want to look back for it. We're going to have to import file in the java.io and then import our scanner as well. Once these are both imported, it'll work. Now what we're going to need to do is make a while loop that runs as long as there's a next line. We'll have while our file.has next, that way it'll get the next thing, and then inside of here we'll do our tree.insert. This instance right here is what we are using, so tree.insert, and then we want to do our file.next int, because all we're doing is we have a file with integers like this separated by a white space, and that's going to be kind of like the break that'll move to the next one. There's a specific word, but I forgot what it is exactly off the top of my head. We are going to want to create a new method. This insert is going to be different from this insert. This is for an object, and this is for our insertion that's going to correlate right here. After we're done with this, we're just going to want to return our tree, and that's going to finish this method right here. Inside of our integer, we have the next int that we're passing in. So what we're going to do is we are going to set our root to this, and this isn't going to be the root for the tree always, it's just going to be the current root that we're looking at. So we'll do root is equal to, and we'll have our insert, our root, and then the next int as well. So we're passing in the root, whatever the root is that is stored, and we're passing in our next int into this insert. Now this insert is going to be where we are actually inserting into our tree. We need to create a local variable for root, which is with our node right here. So all we need to do is come up here and make a private node root, and that will solve this problem. We can create our insert method. We can hover down and create method right here. It's going to be a private node insert, and then we're passing in our node. We'll just call this root, and then we are going to pass in the next, and we'll call this next int. Now this root is not going to interfere with this root, because whenever we are looking at the root inside of here, whenever we're referencing it, we are going to be referencing the one that's local right here, unless we do like this dot root. So that's just important to keep in mind. It won't cause a naming conflict, though it's not always the best practice. So we could do like C root. That might be better for like current root. That way we have better practice. Inside of here, what we're going to want to do is when we're inserting, we first have to do a few things. We have to see if it's empty. And if it's empty, we'll just make a new node. And then after that, we can check if the data, the new data that we're passing in, is greater than or less than our current root. And if it's greater than, we know that we're going to insert it to the right. If it's less than, we're going to insert it to the left. So let's just start out with that. If our root is equal to null, we are just going to want to be inside of here and return a new node, where our new node is going to be the next integer, right? Because the next integer is really our current integer, what we want. This is not going to be like an else if statement, because we want to check this after we do if our root is equal to null. So if our next integer, we're going to say, is less than the current root dot data, we want to insert to the left, right? Because the next int is less than our current data, so it's smaller than. So what we're going to want to do is do our current root dot left. So we're going to get the node on the left, and this comes from our node class where we have our left here. which we'll be storing this data in, is equal to, we want to insert this to the left, so we're going to do insert, where we pass in the current root dot left, and then we're going to also pass in our next int. That way we can compare it. If our current root has a left, we want to compare it to that to see if it's smaller than that. We would keep comparing it. Otherwise, we'll be in this else if statement, and we're going to say else if, and this is going to be very similar, but we'll say if our next int is greater than our current root dot data, and if it's greater than, what we're going to want to do is be inside of the right. We want to insert to the right. And just like how I have in here with no brackets, we actually don't even need brackets in here. And that is because we just have one line of code. In fact, we can just put this right here on the same line. And same thing with this. We can put it on the same line. This frees up space and makes things a little bit easier to read. We can see if root is equal to null, we're going to return here. If this, we are going to execute this. Else if, we are going to execute the following. And I like to tab them to put them all together. That way we can easily read this. So what we can say is else if our next int is greater than our current root.data, we can just copy this here as well. And we want to change everything from left to right. So that is how this would look. After we do this, we want to update our height every single time. So we're going to do update the tree height, and we're going to need a new method for this. Updating the tree height, we're going to do the current root dot height, and we're going to set it equal to, we want to do 1 plus, that way we add 1 to the current height. We have to increment it every single time. We want to get the max height of our left or right, because we don't want the minimum height, we don't want the possible height between the two, we want the maximum height always. So we'll create a method called max, and we're going to create a method called height that gets the height of our actual datas. So we have root dot left we'll pass in, and then we'll also pass in the height of our root dot right. So these are your two methods that we're going to have to create. So we're going to create this method right here, and then we're going to create our max as well. When Eclipse auto-generates these, they're not always 100% correct, so we will want to correct them. We'll start out with this height one right here. So we're going to do private int height. We have our node left. Inside of here, what we're going to want to do is return our height. And we have left passed in just because it's left right here. But what we'll want to do is just have an n for our current node that we're looking at. So we'll do cn, current node. And we're going to want to return the cn dot height. Remember, this is a variable that's inside of here that we're going to be updating. That's what we're returning. If our cn current n is equal to null though, we just want to return the height of 0, because that means that we're going to be in this first if statement right here. If it's empty, we have to make the new node. So if cn is equal to null, all we're going to do is return a 0 like this. Otherwise, we're going to want to return this. So we can even put this in an else statement right here and do our returns like this. That's going to be in our private int class. Next, we're going to be looking at our private int max right here. So we want to return some max value, and we're just going to do an if statement for this. Instead of our private int max, we're going to return. Now we're going to do something very similar to what we did here. However, there's a simpler way to do this. We have an if else statement, but we're going to do it a different way. This way is a little bit cooler. So if our height of the left, which we're going to have here, we're passing in the root left versus the root right, so we'll call this L. Remember, these were auto-generated, so the naming is a little bit weird at first. If our height L is greater than the height of our R, we are going to say that we want to return our height L. Now this works by basically saying we're comparing these. Is this true? If it's true, return this. Else, which is going to be our colon, we want to return the right. Now we can implement this same structure here. It's giving us an error right here. It says we have an undefined operator, and that's because both of these are classified as objects. I think that's because that we have an object right here, though our private node insert should be fine. Maybe it's because we have an AVL tree here. I'm not 100% sure why it automatically declares it, but not an object just like this one should be an integer. We say we had an object right here, I believe, as well. These are both integers, and we're comparing them like this. We can't compare objects like that. We have to compare integers. Now, how would we do that in here? Well, in here, we're going to say we want to return if our cn is equal to or null. And if our cn is equal to or null, we have to check this, and we're going to want to return a 0. Else, we're just going to return the cn current node dot height. With this implemented, we can just get rid of all of this, and we can see that it's much easier. Now, getting rid of the parentheses or the brackets, we can't do that here like we have done with our if statements. So that is how we would do a simple if-else. We could just write it like this, much simpler to implement. And that is going to be our max method. After we get the height, what we're going to want to do is get the balance of our tree. Because if our tree is unbalanced, we are going to have to rebalance it, which would be the next step. So we have balancing the tree, and then after this, we are going to have scenarios for our rotation. And this stems from after we check our balance. So balancing comes first. We'll make a new method in here. We're going to store it in what we call balance. So int balance is equal to, we'll call this get balance. So we're going to make a getter that gives us the balance, and we're going to pass in the current root. So now we can hover over get balance and auto generate a method. We'll see if this one is more correct. Inside of here, we have a private int get balance, and they pass in the node in our current root. Now this should be okay because we're having an integer here that we're returning, and it is of type node. Inside of here, we're going to check if our current null and node is null. If it's null, the balance is going to be 0. Otherwise, we're just going to return the height of the left minus the height of the right for our current root. That will establish the balance. We've looked at this previously in the notes, so on the theory about how to do this. So inside of here, what we're going to want is another simple if-else statement like this. We're going to want to return our current root equal to null. And if our current root is equal to null, we want to just return 0, right? Because there's nothing here. Otherwise, we're going to return the height of our current root dot left. So we get the leftmost minus our height of the current root dot right. And that should simplify this. That should be our return statement. And that's going to be it for our get balance. So this is how we would write our if-else for our very simple if-else. Once we have all this done, we're going to have to look at our rotations. So now we're going to do the scenarios for rotation. We know that if we're on the left side, we're going to be, and we have an imbalance, we're going to have some positive value, whether it be like a 1 or a 2 or more. If we have a right, we have an odd value. So that's something to keep in mind. So first, with our scenarios of rotation, what we're going to want to check is our balance on the left. So if our balance is greater than 1, which means we are again going to be on the left, and our next int, which is the value that we are passing in, is less than our current root dot left dot data, we are going to have to rotate this. Now, how are we going to rotate this? We've gone over the theory before, but we're going to say that we have some current root, we have data on the left of it, which would be right here, and our next int is less than that current, so it's going to be right here. Well, all we would have to do to rebalance this is rotate our current node right here to the right. So we would do a right rotation, and then from here to here to here, it would balance this out, because now this would be here on top, and then this root would be like right here, and that would be right here, the one that we are, or next int that we're looking at. So what we're going to want to do is, and we'll come over here just so we can make everything a little bit easier to see, we're going to want to return the right rotate, we'll call it just a right rotate, where we pass in our current root, because we are currently rotating it around there. Otherwise, we are still going to be in here, because what if our next int is greater than our current root? So we can copy this, we're going to have the same balance factor, and we can push this over so that everything is the same, but this is going to be greater than. So balance is still greater than 1, But if our next int is greater than our current root left data, so we have our current root here, we have our left data, and then our next int is greater than, so it's going to be over here. Now for this one, it's going to be slightly different. So what we're going to want to do is, for this, we would want to rotate the left root. We would rotate it to the left so that the larger value is right here, because this larger value is going to have to go up here. This one's a little bit harder to see. So what we basically have here is some current root. We'll say it's 10. And then from here, we have our current root left data that we're comparing it to. So let's say that this is 9. And then if our next int is greater than this, we'll say that being passed in, we have 11. We would have to rotate this to the left. So we would pass in our current root left, and we would rotate it to the left. So we would have 10, then this would come up. We have our 11, and then we have our 9. That's the first rotate. That's rotating it to the left. And after this, what we're going to want to do is rotate this current root to the right. So this would come down here, and we would have 9, 11, and 10. So we're going to want to do return, and we don't want to do the right rotate yet, because first we're going to have a left rotation, but then we'll have a right rotation. Inside of here, we're going to have 2 lines. So we can come here, we'll still come to the end over here, and what we're going to want to do is do a root dot left, because we want to rotate the left, right? So the left is now going to store the left rotate of the root dot left. And we can see that in this drawing right here. So the current root left is going to store the left rotated root dot left. So that will store that. And now after this, what we want to actually return is the right rotation of our current root. So we're going to return that here. That's going to be our if else statement. And it's probably easier looking at it now to just write it like this. So we have our if like this, we have our else if, and then we'll just move all of these back over. That's a little bit neater. We're going to code out these methods in a second. We have another else if, and this is for when we're looking on the right. So when our balance factor is less than a -1. When it's less than a -1, that's when we have some issue. We're going to have our and in here, and we're going to do it when our next int is less than our current root dot, and we're going to, instead of look at the left, we'll look at the right data. So inside of here, it's going to be similar to the first one for this. All we're saying is that we have some current root, and then we're looking at the right of it. And if our next int is less than, well, all that we're going to want to do is rotate our root to the left so that this is going to be on top. So inside of this else if, we'll just return a left rotate where we pass in the current root. Our last else if is going to be a little bit more challenging. Inside of here, we can pass this in as well. So we have else if, we have our balance factor. Now this is, instead of less than, going to be greater than. So it's the same scenario as what we had drawn out here. It's just the other way around. So we have our right, where we have a current node, and then we have something to the right of it, and then this next int is greater than it. So what we're going to want to do is we're going to want to store in the right rotation of the root dot right. So we'll rotate that, and then we're going to rotate it left. So it's basically just like this, except the opposite. In fact, we'll just copy this here. We'll have these brackets in here. We'll paste this in. Instead of root dot left, we're going to store into root dot right, and we're going to do a right rotate, and then we have our left rotate here, where we do the current root. And that should be our entire method for the insertion. All we have to do now is make these. So we're going to create our method right rotate, and then we're going to create our method left rotate as well. Now we are going to write these methods. We're going to be looking at a right rotate first. And for the right rotate, this is when we have something like the following. We have like a 15 here, then we have a 12 here, and then we have another value. This by itself is okay. because we would have, if we were looking at this, a 0 and then a -1. So we have 0 minus a -1. This is going to give us a balance factor of 1, which is totally acceptable. What's not acceptable, though, is the following, where we have another node, like let's say 9. And that's a scenario that we have in this top part. So we have the current root as 15, current root.left.data is 12, and if next int is less than this, well, it's going to be on the left side. So we're going to have 9, 12, and 15. Now, we know that when we do our balance factor, we are going to have a 0 for something that's here. We have a -1 for null. So we're going to have 0 minus a -1. That's going to give us a 1 here. And then we have 1, and then we have a -1 because there's nothing here. So we have 1 minus a -1. That's going to give us 2. Well, that's not acceptable. We can see that it's higher on this side, the left. So we're going to rotate to the right. This is when we would use a right rotation. Now, for a right rotation, what we're going to have to end up doing is we want this 12 right here to be in the middle. So we wish to end up with something like 12, 15, and then a 9. And this can be attached to like other nodes in our tree, whatever have you. We're just looking at this part right here. If it's bigger, we would use like this else if right here, where first we would rotate the left, and then we would rotate to the right. So that's if we have a bigger problem. But we've discussed this a little bit earlier. It's kind of the same situation, and it'll become apparent when we do the left. So for this, the right, what we're going to do in our right rotate right here is we're going to say we want to mark these. We are going to have our current root, that's already given to us right here. We want to have our left current root, which is this 12 right here, the part that we're rotating around. So we'll just call this L. And then what we also want is, let's say we have some value right here we need to account for, right? And if there's some other way that the node was not balancing out. So we'll just put like N for some node right here. Well, this would be like our R. So when we're doing a right rotation, this is the current roots left, right. So we can write this in our code. Inside of here, in the right rotate, we are going to set our node L, the left, to be equal to the current root dot left. So that's going to give us the left one. And then we have node R, which is the right, and that's equal to the current root dot left dot right. So we get the right of that. And that's going to give us this right here. Now we are going to need to reorganize this and update the height. So we know that the current root is this 15, right? And now it needs to be to the right of our L. So we're going to say that this is going to be L dot right is equal to the current root. And we can just translate that into our code. So we'll say L dot right equal to current root. And that will take care of that right there. Now, we also have to take care of the left-hand side. And this is for the current root dot left. This has to go somewhere, right? This value right here. And if this value was like, let's say a 13, we need to move it. Now, this 9 doesn't have to move because as we've shown here, this 9 is just going to stay with this 12. These two are bound together like this. There's no need for it to move. The 15 needs to move. This 13 also has to move. And the only way for this 13 to go is right here, just based on our searching, based on our balancing of trees. It can't go anywhere else. So what we're going to have to do is we are going to say that our current root, because this is still our current root right here, the 15, we've designated that as the current root. We're going to say that our current root dot left, because this is what it is equal to whatever this is, which is our right, this R right here. So inside of here, we will have a current root dot, let's just double check this, our left is equal to the R. Now we just need to update the height. So we're going to say that our current root dot height, and this is the current node, again we have to update this, is equal to, we want to take the max height. We've done this before, we wrote our method from this earlier, and then inside of here we just want to pass in the height of our current root dot left, and also the height of the current root dot right. So we have both of these passed in, and that's going to give us the total height. Now we do have to add 1 to it. Now we also have to update our 12 because we can see it moves up. So our 12 is the L. So we'll do L dot height, the height of this specific one, is equal to, and then we're going to have the max of the height, and inside of here we want the left of our L and the right of our L itself. So the part right here. So inside of here, well actually not inside of here, because that's important to note. We're not looking at this old part, we're looking at this new part right here. So we're going to have the height of our L dot left, and then we are also going to have the height of our L dot right. And since this is being added by 1, we are going to add 1 to it. So that's going to be our right rotate. And then once we're done with this, what is our new current root? It's going to be 12. It replaces the 15. So we're just going to return our L. And that's it for our right rotate. Next, we're going to look at our left rotate. In preparing for this next section for our left rotate, just doing this out here, the theory of it, I've noticed a mistake. If we have something like this and we want to rotate to the left, well, we can't, because this is going to end up giving us, if we rotate it, a 15, because we have to rotate around that, and then we have a 10, and then we have a 12, which is obviously incorrect. So what this means is I have these two statements backwards. I was looking at them as if they're the same here, but they're not. If our next int is greater than, that's when we just simply do a left rotate. And if it's less than, that's when we do this entire part right here. And this is because if we were to rotate it to the left when it's like this, where our 12 is less than our 15, like how we previously had it, not where our integer that we're passed in is greater than this, we are going to get this, which is incorrect. However, if it's greater than, we're going to have our current root, we are going to have 10, we are going to have our 15, which is our R, and then we are going to have like some null value, and then we have our, let's just say 16, because it has to be greater than. This is where we want to rotate to the left, and we're going to rotate around our 15. So our 15, we're going to have our 16, and then we're going to have our 10. This works, unlike this right here. That does not work. So that is how I would go about fixing that, just looking over at it once again. So from here, what we're going to want to do is, we know that we have our R that we're rotating around. So this is just going to stay here. Now our current root needs to be on the left hand side for a left rotate. So we're going to set our r.left to be equal to the current root. So this place is now our current root. And then we can leave this 16 simply as is. However, we do have an L right here, and that L is going to be this null part, right? And to balance this tree, we have to put it somewhere. Well, this null that's stored in our L is, we know it's greater than our 10, right? So it's just going to go right here to the right of it. And this is our current root still. So we're just going to set our current root dot right to be equal to our L. So now we're going to code this out. Coming down to our left to rotate, what we're going to do, again, we can look at this right here. We have our R that we need to store. So first we're going to set our R equal, and it's a type node, so that's important. Type node R is equal to, we have our current root dot right. So we'll just write that in here. So as croot dot right. After this, we need to store our left. So we have node, we'll call this R, and it's equal to the current root dot right dot left. And that'll give us that value. From here, what we're going to want to do is move our current root to our right's left. So we're going to do r.left is equal to the current root. And after this, we need to do our null part. So that means if we look here, we have a current root right here to the right. So current root dot right, and this is equal to, we have our current root dot right dot left, and that's just simplified as L right here. And we can write that in. Now is where we're going to want to update our heights. Inside of here, we have current root dot height. Now the current root height needs to be updated. We're going to take the max of the left and we're going to take the max of the right, and then we're just going to return whatever that is and then add 1 to it. Just like the previous one, it's whatever height's below it plus 1 because it's above it by 1. So what we can do is come down here and copy this and paste it in. It's going to be the exact same thing because again we have our max here, and then we have our left, we have our right, and then we add 1. Now we also have to increment our r because that's the new root, and in fact we are going to return our r for the left rotate because that, again, this r is the new root. So what we're going to do is do r.height, and this is just the same exact thing. Where we have our max height, we have to find the height of whatever's below it and then just add 1 to it. So we can actually just take this and we can paste it into here. That's going to end our left rotate, and we've completed our right rotate. Now, what happens if we have something like this, where our next int is smaller than? We can demonstrate that right here. So let's just say we are going to do the bottom one, where, and this is basically going to be the exact opposite for the left dot data. Let's say we have our current root, which is 15 right here. We have our current root right dot data, so this has to be like 16. We'll just keep it 18 so we can have some room in case we need something on this side. Now our next int is less than this, so our next int is 17. This still would need a rotation because this is a 0, we have a -1, so this is going to be a 1. We have 1 minus -1, that's going to give us a 2. And since it's a 2, we're going to need to rotate this along here. Well, if we rotate this, we're going to have 18, we are going to have a 15, and we would have a 17 if we were to do it along just like this. But this isn't right. So what we need to do instead is we need to store inside of our right hand side the right rotation, so like right here, of the right rotate. So we are again gonna, not here, we're gonna rotate to the right of this, and then we're passing in our root dot left, so whatever is to the left, meaning this part right here. So we'll go around, and then we just want to return this, and once we store it in our root dot right, whatever value we get here, we're gonna push it to our left rotate, and we're pushing in the C root because now this is modified and this is changed. So it's a little bit more complex than the other one, but it's a little bit harder to explain for me also and to get, but the basic one is pretty simple itself. Now all we have to do is come down and print. And to print everything out, we want to use nodes and we want to use linked lists, and we can put this all in a queue. That way our queue can slowly empty when we print everything out. So we're going to have node, we'll just make a new node, and we're going to set it equal to the root. So using our node class, we are getting some just arbitrary name that we make called node, and we're setting it equal to the root. So that is going to have the entire thing inside of here. First thing we need to checking if it is empty. So just to do this, we'll say if our node is equal to null, all we want to do is return, because there's nothing to do here. Otherwise, we are going to be in a queue. So we are going to have our queue. It's going to be of type node because we're going to store our nodes inside of here. We'll call it queue and we're going to say equal to new. This is going to be in a linked list, and we don't need to specify the type in here. We're going to need to import our linked list, and we're going to need to import our queue. And this is going to be for this little queue right here. Now we want to add into it. So we'll do queue.add, and we want to add this entire node right here that stores our root. We could easily just put if our root is equal to null, or if this node right here is equal to root, so queue.add root, and then check if there's something here. But it's better practice to just put it in a variable, which is what we're going to do, my thought process. So we have queue.add node, and then here we're going to do queue.add and then a null. So we have a stopping point at the end of our list that we can use. We know when to stop. Once this is done, we're going to run this as long as our queue is not empty. So while queue dot is empty and we have a not in front, we're going to be inside of here. Now we want to take our current node and examine it. The easiest way to do that is by using a queue poll. That way it also removes it when we're done with it. So we're going to do node, and we'll call this current n for a current node, and it's equal to queue dot, and we'll pull up the poll class. It returns the head of the queue or null if our queue is empty. This is good because we want to run it as long as our queue is not empty. So we're going to have our queue.poll here. And then we are going to have an if statement. So we want to check if our current n is equal to null. And if our current n is equal to null, we should also check if our queue is not empty. We don't want to put these on the same line, because if we do like if current n is equal to null and the queue is not empty, then if our queue is empty, it'll skip this and not execute, which we want it to at least come in here if our current is equal to null. So if current is equal to null, and if our queue is not empty, so queue dot is empty, but we have a not in front, what we're going to want to do is have a queue.add, and we're going to want to add a null, because that means that our queue should be null. It should be done. It should be empty. And we'll just do a system.out.println after this. So that's going to be it for that. Otherwise, if we don't want to do this, and we should have brackets around here, if we don't want to be in that if statement right here, we're going to have an else statement. So this is when our current does not equal to a null. We can say if our current dot left, so we are going to check each of these. Current n dot left does not equal to null. We want to print this out, right? So to print it out, we need to add it to our queue. So we're going to add to the queue current, and then we'll have n dot, we're looking at the left, so we'll do left here. After this, we have another if statement. We don't want an else if, because we want to also check this. If our current dot right does not equal to null, we're going to be inside of here, and we're going to have a queue.add, and into here we're going to add our current dot right, and then we can end this line, and that should be it for here. As a matter of fact, we can just take out these brackets because it can be on a single line. Same thing with this one. We don't need these brackets, and that'll just make it a little bit cleaner. So these are two if statements for the left and for the right. All we need to do now is print out our information. So we want to do this for each line. So we're going to do this inside of our else statement. We're going to have a system.out.println. Remember, this is only going to happen if our current is not null. So if we have something to print out. Otherwise, we're going to come in here and we're going to end. So this is going to be like the ending statement. Instead of our print line, we can have a parenthesis, we can have a space, and we're going to append to it our current dot data, because that is what it's asking us for. Then we're going to want to append to this just a comma, where we can append to this the current n dot. It's asking us for the height next. We can have another comma and a space, and we want to append to this the balance factor, which hopefully will be less than 1 if we were to do this correctly. And that's going to be just stored inside of our current n. And then here we are going to just add parentheses and close this up. So this is what our print line is going to look like. And that should be it for our code. I do have a text file inside of our lab 7 AVL. We have our input right here, 10.15.6.3.8.9 is what we have. So we can run this and see what we get in our AVL main. It looks like I made a mistake when I was explaining this. The 66, 67, 54, all these lines have problems in it. And the reason why that is stems from this naming of this C root right here. Now, inside of here, it's fine. However, outside of here, when I called this roots, and I called everything C roots, everything else C root, that's where we ran into some problems. So like here, everything has some issues. So what we're going to do instead is just find our C root and replace it with a simple root. We can replace all. Another problem that I was looking at when just debugging this is that we probably don't want this print line here instead of just a print while we run this entire line, so that we print this on the same line. That was not the issue why it's not printing, but that is just something to keep aware of. And I found another issue. Don't know if this is the exact one, but instead of returning null right here, we need to return a root. If we return null, well, we're just obviously not going to print anything because there's nothing to print. We want to return root so that we can return everything that we have here. In doing this, we see that we get an 8, we get our 6, 10, 3, 9, and 15. And so this was the main problem right here. Make sure that we should have initialized this earlier where we would want to return this root. Or declared this right here where we want to return. Not initialized, but declared. That's going to be it for this code. I'm going to quickly run through it all. So we have our main method that calls everything. We have our class node where we are using to actually make this tree. This is kind of the skeleton of it. And then here is all of like the organs, the meat and everything inside of here. All of our code. Our small insert here, where we're reading the actual file in here, we're inserting into our tree. We're doing our insert, which is checking a lot of things, and then we have some helper methods with our rotations, our balance, our max, and our heights down here, and lastly our print. So that's how we would do this code and how we would look at this material.